A linear partial differential equation is one where the unknown function and its partial derivatives appear to the first power and are not multiplied together. The general form of a linear partial differential equation is a1xyz del u del x plus a2xyz del u del y plus a3xyz del u del z up to an xyz u equal f of xyz, where u is the unknown function. a1, a2 up to an are functions of the independent variables. They do not involve the dependent variable u. F is a given function which is forcing term. The equation is linear because u and its derivatives are of first degree and there are no terms where u is raised to any power or multiplied by its derivatives. Examples of linear PDEs: heat equation, wave equation, Laplace equation. Nonlinear PDEs. A nonlinear partial differential equation is one where the unknown function and its derivatives appear with powers higher than 1 or are multiplied together. The general form of a nonlinear PDE is f of x, y, z, u del u del x del u del y up to del 2u del x2, which is equal 0, where f is some nonlinear function involving the unknown function u and its derivatives. This equation is nonlinear because the unknown function and or its derivatives appear in nonlinear terms, that is square terms, products of derivatives, etc. Examples of nonlinear PDEs: Navier-Stokes equation, Burger's equation. Key differences between linear and nonlinear PDE. Linearity. Linear PDEs do not involve any powers or products of the unknown function and its derivatives. Nonlinear PDEs do. Superposition principle. For linear PDEs, if u1 xyz and u2 xyz are solutions, then any linear combination of these solutions, that is c1 u1 plus c2 u2, is also a solution. This principle does not hold for nonlinear PDEs. Solution behavior. Nonlinear PDEs can exhibit complex phenomena like shock waves, bifurcations, and chaos, while linear PDEs often have smoother solutions. Properties and behaviors of linear PDEs. Superposition principle. The superposition principle is a key feature of linear PDEs. It states that if u1 xyz and u2 xyz are solutions to a linear PDE, then any linear combination of them, say c1 u1 plus c2 u2, is also a solution to the same equation. This allows us to build more complex solutions by adding simpler solutions together. Well-posedness. Linear PDEs are often well-posed, meaning that a solution exists, the solution is unique, the solution's behavior changes continuously with initial or boundary conditions. Solution methods. Separation of variables. This method works well for linear equations with simple boundary conditions. The idea is to separate the variables uxt equal xx and tt and then solve the resulting simpler ordinary differential equations. Green function, a powerful tool to find solutions to linear PDEs. It involves representing the solution as an integral of the Green's function. which solves the equation for a point source over the domain. Fourier series or Fourier transforms. These methods are often used to solve linear PDEs, particularly when the problem has periodic boundary conditions. Properties and behaviors of nonlinear PDEs. Complexity and phenomena. Nonlinear PDEs are much more complex due to the interactions between the unknown function and its derivatives. These interactions can lead to fascinating phenomena such as shock waves, bifurcations, chaos. In fluid dynamics, solutions to nonlinear PDEs like the Burger's equation can develop sharp discontinuities known as shock waves. This happens because the nonlinear term causes certain wavefronts to stiffen over time until they form a shock. Nonlinear equations may exhibit multiple solutions for the same set of boundary conditions, leading to bifurcations, changes in the qualitative structure of the solution. Nonlinear PDEs can give rise to chaotic behavior where small changes in initial conditions lead to drastically different outcomes. This is evident in systems like weather prediction models, turbulence, etc. Solution methods for nonlinear PDEs. Solving nonlinear PDEs is generally harder because of the lack of linearity. The techniques are method of characteristics, perturbation methods, numerical methods. Method of characteristics is particularly useful for first order nonlinear PDEs. It transforms the PDE into a set of ODEs along specific curves, which are characteristics in the domain, making the problem more manageable. Perturbation methods are used to find approximate solutions to nonlinear problems by assuming that the solution can be expanded in terms of a small parameter. Many nonlinear PDEs do not have closed form solutions, so numerical methods, finite difference methods, finite element methods, etc. are commonly used to approximate the solution. Examples of nonlinear behavior. Navier-Stokes equation. It describes the motion of fluid substances like air and water. These equations are notoriously difficult to solve due to their nonlinearity and have remained unsolved in general cases for many years. They exhibit complex behaviors such as turbulence, where small changes in initial conditions can lead to widely different outcomes. The Navier-Stokes existence and smoothness problem, one of the Millennium Prize problems, asks whether smooth solutions to these equations exist in three dimensions. Burger's equation is often used as simplified model for shock waves and turbulence. For certain conditions, solutions to this equation can develop shock waves where the velocity field of fluid changes abruptly. KdV equation. It describes the propagation of solitary waves in shallow water or certain types of plasma. The equation is nonlinear but has exact soliton solutions, which are wave-like solutions that maintain their shape and speed as they propagate. Nonlinear PDEs like the KdV equation show how wave phenomena can be more complicated than simple linear wave equations. Thanks for watching. If you have any question, please drop in the comment box.